Okay, so today, like I said, we're going to talk about our final topic. This will take more than one class. There's no way we get this done today. Multiple regression. So last time that we were talking about a simple one-to-one variable relationship. No, sometimes we are. I say often. It's probably a little bit of an overstatement, but yeah, I guess often enough. We're interested in a simple one-to-one variable relationship. So, I don't know, height and weight. You know, your MD is actually really quite interested in the height and weight thing. It's a pretty good predictor. It's the way to see if you're overweight or not. So height and weight makes sense, right? So the way some of those models I think are built are a little odd. I think I come out morbidly obese. I don't know. Not quite. So let's say we've got some relationship and we have an R, that's the correlation coefficient of 0.5 for some relationship. And in fact, that would be something that someone in the sort of social science part of psychology would be pretty happy with. That's a pretty high correlation. Typically, they're happy with correlations really above 0.3. And that's fine. So remember, R is the covariance of x and y divided by the standard deviation of x times standard deviation of y. So it's about standard deviations. So the question is, how much variance is accounted for by one variable in the other? How much variance in x is accounted for by variance in y? Correlation doesn't tell us that. Correlation tells us about the relationship itself. But how much variance is accounted for? Well, this is about standard deviations. So we'll just square it. So we'll square r squared then, little r squared, call that equals 0.25. So proportionally, 25% of the variance, or 1/4 of the variance in x, is accounted for by variance in y. I can think of two variables like this pretty easily, I think. If you think of IQ and income, they're correlated at about 0.5. Meaning that about 1/4 of the variance in income is accounted for by variance in IQ. Okay? That shouldn't surprise you. No one said life was fair. It's actually a little bit harder. The correlation between IQ and scholastic achievement, however you want to measure it, GPA, you can measure it that way, you can measure the number of years of education you get, things like that, is about 0.6, meaning about 36% of the variance. And that, again, shouldn't surprise you that smarter people do better in school. No. Smarter people get better jobs. Really? Yeah, I mean, that's the way the world works, right? So, but 0.5, 25%, that's not bad. In fact, you should be pretty impressed with yourself if you can explain 25% of the variance in one variable with variance in another variable. It actually is kind of neat. It's kind of cool. I mean, but that also tells you something. That tells you there's 75% left that you haven't explained. Now, are you going to get to explain 100% of the variance? Well, probably not. Probably not, especially in the sort of, as I said, the sort of more social science parts of psychology. It's just not going to happen. There are too many variables, and the interactions, and I don't mean statistical interactions, I mean the way the variables interact, the way they come together, are so complicated that explaining all the variance is not going to happen, bro. In more natural science, I hate this distinction, but we'll use it anyway, areas of psychology, you do end up explaining a lot more variance. But the inputs and outputs are a lot better defined. Right, so if you look at some of the work on animal timing, I know one paper, there's a paper hanging up outside there, timing black-cap chickadees. We explained, I think, 99.8% of the variance in timing behavior. And that shouldn't impress you. Timing behavior is very specific. So that's really pretty, it's not that hard to do. And in fact, now with timing stuff, they're down to explaining 0.001% that's left. Right? But again, the inputs are a lot better defined and the outputs are a lot better defined than they are in the sort of social science area. So if you can explain 25%, you should be pretty pleased. But there's still 75% left, and if you're innately curious at all, and as a scientist you should be, you go, well, what's left? How do I explain it? So you understand the point here? Yeah, you get 75% left. Let's try to explain it if we can. So there must be variables that account for the rest of the variance. Okay. Must be other ones. There's going to be at least one. There'll be at least one. Now, the way we deal with this is we actually bring them into the model. So now what we're going to do is we're going to have two predictors, not just one. Before we had one predictor, right? The equation's still up here. Y hat equals a plus bx. Remember I said the other day, let's change that to y hat equals b sub 0 plus b sub 1 x sub 1. What we're going to do now is we're going to have y hat equals b sub 0 plus b sub 1 x sub 1 plus b sub 2 x sub 2. We're going to have two x's. That's all. Two x variables. We're going to bring another variable in. So if we've got y, here's our y variable. I don't know what the hell it is, but it's this part of the equation, the thing we're explaining. And then we have x1. Now this overlap is the shared variance, and that's about 20. It's probably about 20%, isn't it? Okay, but there's still all this other variance in y, all this extra stuff here, right? That we can't account for, we haven't explained. Well, let's bring in x2. Now we've explained extra variance in y. So again, as I said the other day, you have to start thinking of variance as a thing, as something you can touch. Something you can hold and love and nurture. That's a little strong, a little weird. But you got to think of variance as a concrete thing, and that's a hard thing to do. I understand that. But here's the variance in y, here's the variance in x1. We bring that in there, the overlap, that's what the overlap is, where one set of variance explains the other. Then this variance in x2 overlaps with y. That's more variance explained. Questions? Yeah. Okay.
So would x1 and x2 not have covariance then?
Yeah, we're living in a fantasy land on Lollipop Lane right now. Yeah, you would expect that they would also overlap. Right now, I'm not doing that because the world gets much more complicated. We will get there. But yeah, of course, you'd expect that x1 and x2. Like, let's say that y was income, and x1 was IQ, and x2 was, what's something else that correlate with income? Besides IQ? Age, yeah, that's actually pretty good. Because the older you are, the more money you make. Sure, it makes some sense. Does age correlate with IQ? There's probably some variance there where they're going to overlap. Yeah. Right. So yeah, in the best of all possible worlds, no. But we don't live in the best of all possible worlds. So yeah, really it wouldn't work that way. Yeah, sorry, Christine.
So there'd still be some variance that you haven't accounted for in that model, right?
Yep. All this stuff where y is not overlapping with x1 or x2, that's unexplained variance in y.
So say we're getting more technical.
Yeah.
I don't know if this is an actual thing.
So that's fine.
But say you add 4 more circles on.
Yeah.
And they all overlap, so all of y is covered.
Yeah.
Then do they bleed into the ones they're touching, or can you pretend those are really squares?
They wouldn't be circles necessarily, right? So you could. So here's another way to look at it, and I'm glad you brought this up. Here's another way to look at it. We can think of it as you probably can't. No, you can see that. So it's over here. If we have variance in y, instead of as a circle, we're going to turn it into a bar. Okay, so let's call that y. Okay. Now, here's x1 and y. What we're going to care about is not so much. Let's bring in x2 now. Now we're not going to care about the x1 and x2. Well, we can even have them. Let's not worry about them overlapping. Let's worry about extra variance accounted for by x2. So these may overlap, but that's not what we're doing right now. We're just talking about how they overlap with y. And then we have x3, x4. Let's make x5 really small, and there's x6. Do all those other x's overlap with each other? Almost certainly, yeah. You could set it up if it's an experiment that the x's don't overlap, but that's not usually when we use regression. But yeah, that's a good question. I mean, and if you think of it, instead of like a Venn diagram like this, if you think of it in this sort of big stack of variance, if that helps, that's just another way that people used to visualize me. But yeah, we would have different little shapes. Exactly. And they would also have other parts that don't overlap, so you might have some sort of trapezoid here. Perhaps a rhombus. You never thought you'd hear the word rhombus past about grade 6, did you? Well, you just did. You just did. Some sort of quadrilateral. Dodecahedron. Okay, so in general we end up with a model. Just like, well, this was the first one. The one we have on the board here, the y hat equals a plus bx, or y hat equals b sub 0 plus b sub 1 x sub 1. This is what we get now. What? Jesus, don't play me. What's that? Look, y hat equals b sub 0 plus b sub 1 x sub 1 plus b sub 2 x sub 2 plus plus b sub p minus 1 x sub p minus 1 plus e. There are p minus 1 predictors. Okay? There are p minus 1 predictors. P minus 1 x variables if you want. Okay, so it can get big, that's all. It could. If we had 6 of them, it would go up to b sub 6, x sub 6. And p minus 1 equals 6, meaning p equals 5. Or sorry, p equals 7, sorry. There are p minus 1 predictors. As it says right there. So p minus 1 predictor variables. And we have residual. So this is the data set itself. So this is actually, these are statistics. This is your sample statistics. They're calculated. Okay? They are not parameters. There's a bit of a difference. Think about back to the structural model of analysis of variance. Those are actually parameters, right? They're Greek letters. So this is a bit different. You could actually do analysis of variance. We could use these we could use statistics in we want. So that's the model for the data set. But in the population, it's different. It's y equals beta sub 0 plus beta sub 1 x sub 1 plus beta sub 2 x sub 2 plus plus beta sub p minus 1 x sub p minus 1 plus epsilon. These are betas, and then they're not the same as the beta in power. Again, I know, I'm sorry, it's not my fault. I didn't design the world. If I did, it would have been a lot more sensible and amenable to me. Residuals are normally distributed. They're independent of each other with a mean of 0 and a variance of sigma squared sub epsilon. Does that sound vaguely familiar? Like error always is. These aren't actually error, though. They're leftover stuff. Because the population doesn't have error. This is what's left. So epsilon is not a prediction error. It is individual variation. Individual difference. Stuff left over, or residual. Stuff we have not explained. Also note that this says y equals. This does not say y hat equals. This is not a prediction. This is a description of how the universe works. These are parameters. This is saying this is it. This is true. There's no truth, man. Give me that crap. I don't know if I did that for you. Sometimes some of these are just for me. But this is saying this is how the world works. When we're making a prediction, that's different. We're saying that y hat is a prediction. You think it's going to be like that. Could be like that. This is saying this is it. This is how it is. That's a subtle distinction, but it is a distinction nonetheless. Okay? Yeah.
Where'd the A go? Is that now
the what? Oh, the A is now B sub 0, or in this model, beta sub 0. Yeah, that's part of the problem. That whenever regression is introduced to students, and I don't know why this is done, but it's always in textbooks. Starts out y equals a plus bx, and then they say, oh, for multiple regression, now it's b sub 0, which I think it's to make it easier. But it'd probably be easier if we just said b sub 0 plus b sub 1 x sub 1.
Makes so much sense now.
What does?
Because I just looked at it and then I realized that bx becomes a b sub 1 and x
Yeah.
sub 1.
Yeah,
And then the
it's not
a
scary.
is just the
Yeah, the age just that's the intercept. They're the same thing. You just have different names. It's Steve and Eddie. They just have different names. It's the same thing, right? It'd be like calling you by my first name or my middle name.
What's your middle name?
Richard, named after my dad. And then my son's middle name, he's got my first name, and Darwin.
Really?
Yeah, Jonathan David Darwin.
That's amazing.
Yeah, I wanted to name him Darwin, but just didn't totally. But both Isabel and Maddie were like, you can't. It's like being Einstein. No, it's a cool name, but no, I got overruled by the permanent members of the Security Council. And Maddie's middle name is Isabel, after Isabel. And then Robin. It's a great story about a woman that sat with Isabel while she was in labor because I was in Toronto. I had a thesis meeting for my dissertation, and it wasn't like I was just hanging out drawing. Well, have a baby, have fun. I'm in Toronto. No, I was doing work. I rushed home to London. All right, that came from the different names for the intercept. Okay, so you're thinking, how the hell did we get on that? All right, so again, I'm glad it makes sense, Jay. Do you see this? This is, if these are parameters, this is saying, and we're trying to predict, we're trying to guess the way the world works. This is how the world works. We guess the way the world works by building the regression model.
Did you just say those are parameters?
These are parameters. That's the population. Yeah. Because they're Greek letters.
Why does it say these are statistics, not
Because that's the last slide, not this slide. Why does it say exploratory data analysis? Because that's January. Yeah. Okay. Other questions?
Scared to ask a question.
No, I'm having fun. I like you guys. We're among friends. Don't feel bad about asking questions ever, please. Because I want you to. This stuff is really conceptually not incredibly easy. I totally get that. So, and we're going to do this almost completely on a conceptual level because it's really the only way you can do it. Because the math behind this is all matrix algebra, and we're not doing that. Oh, we don't play that. It's not going to happen. I have enough trouble with matrix algebra. It's real expensive.
What does the thing under the thing mean? Yeah.
This here? Yeah. So it's just saying that epsilon, that's the residuals, are normally distributed. They're independent of each other. They have a mean of 0, and they have a variance, and we got to give it a name, so we give it the name sigma squared sub epsilon. That's all it means. And it's exactly the same thing. In fact, it's true of epsilon in an alpha variance model. Right? Errors is normal and independent with a mean of 0 and a variance of sigma squared sub epsilon. It actually looks exactly, it's the same thing. Okay. This, in fact, should look suspiciously like an alpha variance model. Something that applies to everyone, plus a bunch of other stuff that depends on the value of a variable, plus error. Kind of similar. Other questions? Again, I want you to get, if you get this, we have a lot of time. This is the last topic, so I don't move too quickly. I don't want to, perfectly happy. Okay. So what do we get? So if p minus 1 equals 1, we get a line. In other words, if we have p minus 1 predictors, that means we get p minus 1 equals 1. That means we have one predictor. That means that the model is y hat equals b sub 0 plus b sub 1 x sub 1 plus epsilon, or plus e rather, plus error. And you know from elementary, well, high school, I guess, that you get a line. Right? Because if we have there's y, there's x. We get a line. You've done that. You know that. P minus 1 equals 1. There is one predictor. You get a line. It has an intercept and a slope. Right? This is intercept, slope. It's exactly like you've seen in, you saw in grade 8 or grade 9, probably grade 9. Circular functions. Right? You get a line. If P minus 1 equals 2, we get a surface or a plane. Anybody here ever do any X, Y, and Z geometry at school? So 3-way coordinates, not just 2. So you have something that's at depth. You have another axis coming out this way and going back that way. Anyone do that?
No.
Well, think about it. Okay. If the world's two-dimensional, X and Y, we see the edge of this paper, right? That's a line. Right? Isn't it? Now, suddenly the world's three-dimensional. We got a third dimension. Oh, look. It's a surface. That's pretty neat. And you can do that. There are 3D graphs. I know people make 3D graphs for no reason, even though there's only two variables to have, but it drives me, it makes me angry. Well, the ink to information ratio is, don't waste, no need. But sometimes you have 3 variables, so you get a surface. Okay. Does that make sense? Because I have a third dimension. So those two things are pretty easy to imagine. The first one's obvious. It's very easy to imagine. You've been taught XY coordinates, Cartesian geometry, and you've been taught this since you were 13 or 14 years old. You know about it. You may not have liked it, but you were taught it. And again, did anybody learn about 3D coordinates in school? Really? Dan thinks he did, and Jade and Tom. Okay, so some of you have. Some of you have. X, Y, Z. And the Z here now is just X, Y, and X1, Y, and X2. So we're not going to use Z now. What I call it. So the depth one's going to be a different X. Oh, yeah, sure.
Could you give an example of maybe using the model for a sample compared to a population? Like how you
Well, okay. So it's true that we can collect data on, we can do in this room. We can collect data on your, I give you all the weights, the Western Intelligence Scale, and I can get all your GPAs, right? I can do something even easier than that. I can get all your GPAs, and I can get your grade on the last test. I'm going to guess that your GPA correlates pretty highly with your grade on the last test. I'm almost certain it does. Okay. Now, but that's all IQ. IQ and GPA. So we're going to use you guys as a sample. And I've got IQ, Y equals, we figure something out, we do the math, and we get equals B sub 0, whatever that is, plus B1, and I don't know, whatever that value is, it's something we multiply times your GPA to get your IQ. Is that what I said? Now, in the population of students at Algoma University, it actually is true, that big Y, GPA, I think I'm using GPA as the predictor, right? As the predicted, equals some number plus another number times their IQ. That's the model for the population. So that's the difference.
Okay.
Make sense?
Yeah, thanks.
Okay, no problem. Now, it gets complicated if we have more than 2 predictors. Things get complicated with more than 2 predictors. So here we have two-dimensional geometry, which we can imagine. We don't actually live in 2 dimensions, but we can imagine 2 dimensions. That's easy. We have add a third dimension. Suddenly we have depth, so we can now see the depth of the world. With p minus 1 greater than 2, we actually got what's called a hyperplane, and it's in hyperspace. In other words, it's in 4 or greater dimensional geometry. Don't try to imagine it. Unless here's one way you can imagine a third predictor variable. So we have this slope and then this slope, right? Now time becomes a variable, and as time goes, this thing moves. Does that help you imagine? No, it doesn't help me at all. That's what it's going to do. A fifth one you could imagine it could be changing color. I can kind of imagine the time one, kind of, sort of. The color one, my old stats prof, he said he was able to visualize 5-dimensional hyperplanes by thinking of time, so it moved, and then it changed color from cold to hot colors. I can't do that. Dan?
If we get into more and more of these, I guess we run into probably a mathematical equation for existence.
I don't think so. I mean, if you could explain all the variance and everything ever, yeah, but that's not really what we're trying to do. That's not going to, we're not at the level of, this is neither science fiction nor is it armchair philosophy. So, yeah. But I mean, imagining something moving, if that helps you, that's fine. But I think after that, just start thinking of it as an equation. It's okay to think, like I said, I like line and I love lamp as well. I'm glad you got the reference, good. So I like the line, I like the surface, that's great. And even the moving surface I can kind of do. Beyond that, I stop imagining it as a thing. I just stop I just think that this is an equation. Right? So my friend Todd, I was telling you about him, and he did this stuff about predicting the number of cigarettes you smoke per day, and it was some number. Okay, so y, right, equals some number, so that's the intercept, plus some number times the number of years you smoked, plus some number times the years you started to smoke, plus another number times the time the first cigarette in the day, and another number times, what was the final one? How many times you tried to quit? I think that's what it was. So you can see it's just an equation. You could imagine it as a 4-dimensional hyperplane if you want to, but I don't think it helps you very much. So you get a hyperplane in hyperspace. Spin up the FTL drives, Mr. Data. Do your job. I love Battlestar Galactica. It's almost time for another watch through. Almost time. It's in the fracking ship. All right. Ha ha! It's back, baby, and with a vengeance. From a quick tour of Europe, it's back. Analysis of variance. We can find out if we've explained a significant amount of variance. Oh, how do you find out explaining significant amounts of variance? Well, analysis of variance would probably do the trick. So we're going to use ANOVA here. We're not going to do this. This ANOVA is actually, in some respects, quite a bit easier than the stuff we've talked about before. So we have 2 sources of variation. We have variance due to regression. That's the model. The whole model, by the way. So if we have y equals b sub 0 plus b sub 1x sub 1 plus b sub 2x sub 2 plus b sub 3x sub 3, it's explaining the whole thing. And variance due to residual. Wow. Model plus, leftovers. That bloody well better be significant or you've just wasted your time. If you got 4 or 5 variables in there, yeah, it will be. So, we get, that is screwed up. That should say sum of squares regression divided by p minus 1. That should make that think bigger. Okay, sum of squares regression divided by p minus 1. We got source of variation regression, residual, and total. Degrees of freedom p minus 1. That's the predictors. We have residual n minus p. N is the number of, if you want to put this in, yeah, let's call it records. So every time we get, okay, let's say it's just 2 variables, it's number of pairs. If it's 3 variables, it's number of triples, I guess you call it. If it's 4, it's number of quads. So we'll call them records, like a database or a spreadsheet. Number of rows, you can think of it that way. Rows in a spreadsheet or in an SPSS data set. So p minus 1, n minus p, total of n minus 1 degrees of freedom. That's the number of sets of observations, or number of records, or number of rows, if you want to call it that. Minus 1. Sum of squares, I'm not even showing you a calculator. So we're not even going to worry about it, okay? Believe me that that one can calculate the sum of squares. Okay. And then you do an F, which is mean squared regression over mean squared residual. And you should see that p minus 1 plus n minus p, when you add these two together, you get n minus 1. See, because look, p minus p is about n minus 1. N minus 1 equals n minus 1. This analysis, again, is about the whole model. And it's not about individual variables. It's not about is x1 or x2 or x3 significant. And what we're caring about there is x1, x2, x3 significant. Is these coefficients, these b's, are they non-zero? Because if it turns out that, if the model was y hat equals b sub 0 plus 0 times x1, x1 isn't important because it's always 0, right? So we're trying to see if the b's, colloquially, these are known as beta weights. And they shouldn't be because they're b's, they're not betas, but we'll call them beta weights. We should call them b's, but your stat software always calls it beta weights. Books always calls them beta weights, and they shouldn't be. They should be called b's. But that was too easy to understand, so they changed it to beta weights. They're just coefficients in the model. Remember what a coefficient is? Remember that from high school, right? Like y equals 3x plus 7. 3x, the 3 is the coefficient. We're trying to see if this, in this case b1, is significantly different from 0. This doesn't tell us that, by the way. All this says is, all this stuff's greater than this is significantly explains the variance. Well, I freaking hope so. If we got 4 or 5 variables, it better explain a significant amount of variance. So we're eventually going to get to a point where we can see if these beta weights or these b's are significantly different from 0. We're not quite there yet. So this is looking at the whole thing. One thing is the sum of all its parts, except for the e at the end. It's explained variance divided by unexplained variance. Okay? This better be, like I said, how could it not be? Right? That should be non-zero, the thing on the right. It has to be. Okay. So we're going to want to do, but before I move on, question. All right. So we're going to want to do some kind of finer grained analysis. So of course the model is significant, as I say here, bloody well better. We're much more concerned with how much extra variation is accounted for by adding another variable in the model. That's what we started out today. We want to add another variable to explain more variance. So that's what we're interested in. And if we go back over here to our tower of variance on the left here, when we add x2 in, is that a significant amount of variance in y explained? Okay? That's the kind of question we're really asking. And if you look at our On this here, I got x5 as being a little sliver. It might be the case that we wouldn't leave that in. It's too small. It's almost 0. One of the things we can look at is, remember we started with little r squared. We can look at big R squared. This is how much we have variance and why we've explained with the whole model. This is also called the coefficient of multiple determination. And we take the square root of that, we get a multiple correlation. And you might have seen in articles you've read, for papers you're writing and stuff, people doing multiple correlations. That's what this is. So r squared, big R squared, equals sum of squares regression divided by sum of squares total. So you'll often see people refer to big R squared, and they're just talking about how much total variation they've accounted for. We can then take the square root of that and get this multiple correlation, which is pretty neat. So let's add in another variable. So the idea here is we've got, if we have, well, the notion here is if you have a model with 5x variables, so that's y hat equals b sub 0 plus b sub 1 x sub 1 plus b sub 2 x sub 2 plus b sub 3 x sub 3 plus b sub 4 x sub 4 plus b sub 5 x sub 5. If you add a 6th variable in, does r squared go up? Well, it has to. There's sums of squares. It has to be a positive number. We add another variable in. This is going to go up. It must go up. It cannot go down. It could not move at all, theoretically, if there was literally no relationship between the 6th variable and y. Literally no overlap. That's not going to probably happen. So the question is, does r squared go up by enough to make you happy? So you add the extra variable in. Is it enough? Are you explaining enough extra variance? Over here again to the tower of variance. x1 and x2 are big, and we throw in x3, it's good. x4, and we throw in x5. Do we want to do that? Is that enough? Well, I don't know. Did r squared go up enough? What the hell does that mean? How imprecise could one be? Did it go up enough? I don't know. Is it enough for you? And one of the ways you can look at it, you're losing degrees of freedom. It's always about that, eh? Just like, remember you have an extra variable. So there's enough to deal with the loss of degrees of freedom, the increase in complexity. When I add a 6th variable in after 5 variables, it's getting more complicated. If I add one variable in after having only one variable in, another one, like y equals b sub 0 equals b sub 1 x sub 1, I bring in x2, I can even draw the graph. I got a computer could draw a nice 3D graph for me on 2D paper, wonderful. Or perhaps I could 3D print it. Everything's 3D printing. Everybody's excited about 3D printing. If I go from 2 variable to 3, suddenly I got a hyperplane. It gets a little more complicated for people to imagine, or me to even show you a picture. I can't show you a picture. I could. I guess I could have it moving around. An animated GIF. It's GIF. It's GIF. People that say GIF are aligned with the terrorists. Pretty convinced of that. You say GIF, the terrorists are going to win. Isn't it nice to live in a country where we can sit here and have silly arguments about is it GIF or GIF? It's so nice. It really is. I'm serious. So, this is also, see, when you get into practical kind of questions, right? Going from 5 to 6 is not a big deal. Going from 2 to 3 to me is a huge step because I can't draw the graph anymore. So we need to look at something other than r squared, big R squared. Okay, I'm never going to ask you how to do this. But there is a thing called adjusted r squared. And what it is it actually can go up and down because you can see it's weighted by the number of predictors in the model. So adjusted r squared actually does this. As I said, it's weighted by the number of predictors in the model. So it can go up and down. So this is one of the things, in fact, that people use when they're deciding, do I put that extra variable in? They compare it with 4 variables and 5 and see if adjusted R-squared moves. And every statistical method we'll talk about, we're going to see that we put adjusted R-squared in. Okay. So I'm never going to ask you, well, if I asked you what adjusted R-squared was, well, frankly, the only place I can ask you now would be on the final exam, and you can just write that down. But I because you get your notes right. But I could also, I would accept something like a measure of explained variance that can go up or down and is weighted by the number of variables in the model. That's perfectly fine. Right. But like I said, you just write this down. Thank you. Okay. One last question for today. Let's say we have a model that looks like this. This is with x1 in the model, only x1. So it's, and also an intercept, and okay? We've got sum of squares for regression of 50, sum of squares for residual of 80. Okay? That's just one variable. Put that one over there and bring this one in. We've got, this is x2, only x2 in the model. Sum of squares regression of 30, sum of squares residual of 100. So we can see if we wanted to do R squared, we've got 5/8 or 3/10. What about when they're both in the model? Now it goes, we got sum of squares regression of 80, sum of squares residual of 50. Which one do you think is the best model? Well, first, can we all agree on one that's the worst? That's easy. The one that explains the least variance. I think the x2 model. So that would be, again, y hat equals b sub 0 plus, we'll call it b sub 2 x sub 2. That's no good. It's not explaining very much variance at all. Right? Because the sum of squares regression is only 30. So now it comes down to this. Which one of these is better? This one? Just with x1 in the model, or with x1 and x2 in the model? Which one do you think is better? Which one would you prefer? Okay, I'm going to make you vote. And if you don't vote, it's like Australia, you have to vote, or you get arrested. It's true. No, in Australia you have to vote. It's mandatory voting. I like that. Okay. How many people think the x1 is the best model, just with x1? How many people think that? How many people think x1, x2 is the best model? So it's pretty almost unanimous. You like this, you like this. Somebody didn't vote. I saw, I know not all you had your hands up, either, but whatever. He'll be held to pay. Have to go live out in the outback. I think that's what happens. They make you live in the outback. I don't know. It's Australia. I don't know anything about Australia. They play funny football, talk funny names for things. It's a billabong, not a like. It's weird. So, what's going on here? Why did you like, y'all like this one? Why did you like that one?
Because the residual was lower.
Yeah, and that's a perfectly reasonable answer. That's a good model. Residual is the lowest of any of them. I mean, the least, and residual is the unexplained variance. So yeah, is that why everybody else thought too? Yeah. Did anybody pick this one? This one's a line.
Oh.
Lines are nice. It's just like this. I can draw it with a pen. But that's also, those are both decent models. This one sucks. This one's not good.
Yeah.
Okay, so we don't worry about that. But it's nice that on its own it's no good, but together with x1, it makes everybody in this room happy. It's a plane, so we can still visualize it. So it's not that bad, it's not that complicated. Plus, it explains a lot of variance. Here's a question for you. do x1 and x2 overlap? Remember we had the pictures with the, going back to what Christina said, right? Like, do we have the, and also Cassidy, like, do the x variables, do they overlap? Do their variances overlap? So my question to you is, do x1 and x2 overlap? What do you think? Who says, yes, they overlap? Okay, one. At least somebody had the guts to put their hand up on something. Who says they don't overlap?
I don't know.
Okay, Lissa. Lissa's right. They don't overlap. How do we know this? Sum of squares is about unique variance accounted for by the model. Okay? Unique variance accounted for by the model in Y. 50 plus 30 is 80. They do not overlap. If it was 50 and 60 and 80, they would overlap. Or 50 and 31 and 80. Because that means that there is some, but see, these have to be, this is unique. This is 5/13, 50 out of 130 variances. I don't know what the Fishers, perhaps? 30 out of 130. 80 out of 130. 15, 30, 80. Okay. This is one of those cases where we're living on lollipop land in the fantasy land. And in fact, to be honest with you, I would also choose the two-variable model. We got a two-variable model where the two x's don't overlap. It's like, that doesn't happen. That's a fantasy. Plus, it's a plane, not that hard to understand. All right, questions about this? We will talk more about this on Thursday.
I bet you they're all from you. They are.
Okay, so this is where we were last time. So we were talking about trying to figure out which one's the best model. And I was talking about how you have x1 in the model, x2 in the model, or x1 and x2 in the model. And note a few things, that the total sum of squares was always 130. It's not always going to be 130, but in this hooked up example, it's not always, they're going to always be the same. Because remember, what we're doing is trying to always explain, this is the thing where I keep saying always. These are never in the chart where it belongs. Always trying to explain the variance in Y. So, in this case, there's Y, has 130 variances, units of variance, or we could use the sort of column version, which might be a bit better. So, there's 130 total. Just x1 takes care of 50. Just x2 takes care of 30. And interestingly, x1, x2 takes care of 80, and 50 and 30 is 80, and that should tell you something. There's no overlap between x1 and x2, so this is x1, and this is x2. So there's always a constant amount of variance in Y we're trying to explain. Okay. So, like I said, in this case, I think I'd go either with this one here on the far right, which is x1, x2, or just with the x1 version. Because they explain the most variance. You can make an argument that this is just a line and that's a plane, a little more complicated, the plane, but frankly, two variables versus one is not a huge difference. All right. So, we've talked in the past about type 1 and type 2 sums of squares. Remember I mentioned that about when we were talking about missing values in empty cells with analysis variance. So there are things called type 1 and type 2 sums of squares. They're calculated roughly pretty much the same way. Type 1 sums of squares depend on the order variables go into the model, and type 2 sums of squares don't. So I'll explain this in a second, how this is sort of calculated. So let's say we have a three-variable model, x1, x2, and x3. So and when I say that, I mean it's y hat equals b sub 0 plus b sub 1x sub 1 plus b sub 2x sub 2 plus b sub 3x sub 3 plus e. Like, you know that when I just say x1, x2, x3, I'm talking about a model that has all those things in it, right? Okay. And obviously an intercept, as mentioned. So, the type 1 sums of squares for x1 are just sums of squares for x1. The type 1 sum of squares for x2, now x2 is put in, is sum of squares regression for x1, x2. The type 3s, or sorry, the type 1s for x3 is all 3. I mean, that's weird. Because the type 2s almost look more reasonable, don't they? That's x1 given x2, x3 is in the model. x2 given x1, x3 are in the model. And x3 given x1, x2 are in the model. These are conditional, the type 2s. The type 1s are not. Now, if we were doing the calculations and we'd started with x2 instead of x1, the type 1s change. Because it's the order we put them in. The order we started doing the math in. Whereas, that does not happen with the type 2 sums of squares. So type 2 sums of squares talk about unique variance explained in the predicted variable, in y, explained by a given variable. Okay? They talk about unique variance explained. Different. You might look at type 1s and go, well, why are they useful? They have a use when you are when you're building a model, and I'll explain that in a little bit. Because right now, the thing that looks most useful is unique extra variance accounted for, assuming everything else is the model of type 2s. And in fact, typically, you'll be able to, when you see an output from something like SPSS, you get, it'll say your type 1s or type 2s. You're often, you will get both, your type 1s and type 2s. I think the title for the next slide is Useful, Why Should You Care? Well, if there's no correlation between the variables, then the type 1s should equal the type 2s. If there's a correlation, the type 1s don't equal the type 2s. Now, there's always going to be a correlation between the variables, almost always. But you want that number to be as small as possible, that correlation. You want that to be as small as possible. And we'll talk a little bit more about that later. Why you want it to be small. Okay. Now, what do type 2s give you? Type 2s give you the extra variation accounted for by having a variable in the model, given the other ones are already there. So in other words, they're looking at unique variance accounted for by a given variable. They, in fact, allow you to do something kind of neat. They can actually give you something called the coefficient of partial determination, which is really, it's sort of the opposite of R squared, big R squared. Remember, big R squared is just the whole model. How much variance and why we've explained using all of these variables at once. The coefficient of, which is the coefficient of multiple determination, big R squared. Coefficient of partial determination is a way to a way to statistically control for other variants. So we suck the other variants out, and we look only at unique variants. Sometimes you'll see people talk about partial correlations, and that's what this allows us to do. So sometimes you'll see in a paper a partial correlation was done between income and education and IQ. Income and education controlling for IQ. That's a partial determination, coefficient of partial determination, or a partial correlation. Okay. So it's extra variation. So the coefficient of partial determination gives us an extra variation accounted for by adding in another variable. It's about unique variance. It's about unique variance that only it accounts for and nothing else accounts for. Nothing else to be measured anyway. Not nothing else in the universe, but nothing else at least to be measured. Okay? You square it with partial correlation, which is actually kind of a useful thing. Or take the square root of it, I should say. Yeah. Yeah. So again, why does this matter? Well, think about our model. And remember, just like with analysis of variance, everything's going to flow out of the model. All the assumptions, or a lot of them at least, come out of the model. Here's the model, right? Y hat equals b sub 0 plus b sub 1 x sub 1 plus b sub 2 x sub 2 plus dot 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 plus b sub p minus 1 x sub p minus 1 plus e. It's a completely additive linear model. There's nothing in there about two variables together, is there? There's nothing in there mentioning and x1 and x2 together. Nothing. There's nothing in there that says, there's no like b sub 3 x sub 1 times x sub 2. There's literally nothing like that in there. There's nothing talking about overlapped variance between x variables. When we have overlapping x variables, which we almost always do, we are violating an assumption. There's an assumption here. It's explicitly said here that this is how the world works. And the math's going to fall out of that. If that's how the world works, but it isn't, we violate an assumption. So this is a real problem. And that problem, depending on how much overlap you have between x variables, and this problem is called multicollinearity. Multicollinearity. Okay? Multicollinearity bad. Well, lots of multicollinearity bad. Some multicollinearity expected. But let's say let's think about the absurd, because sometimes an absurd example is really helpful. If we're predicting weight from height, that's been sort of a running example we've had, and I think we've all had that experience. You go to the doctor, they weigh you, they say how tall you are, and they tell you to stop eating so much. No one gets told, you're too thin. So, would it make sense to say, okay, well, we measured your height in both centimeters and inches. Let's put both of those in to see if it has any more predictive value. Well, no. They're measuring exactly the same thing with a different scale. You wouldn't do that. It's patently stupid. You're accounting for, what are you doing there? You're accounting for exactly the same variance. You've got one x variable measuring height in centimeters, the other one measuring height in inches. Is that useful? Well, clearly not. In that case, in the absurd example, you're measuring exactly the same thing. You don't want to do that. Okay. So we don't want to have multicollinearity because we're violating an assumption. We have multicollinearity. So what'll happen? It changes the b's, the estimate of the b's, or as like I said, people often call them beta weights, which they shouldn't call them. And the b's are pretty important because those coefficients of the x variables. So remember, like let's make up a model for height and weight. So your weight, that's y, in kilos, should equal some number, right, plus some other number times your height in centimeters. Okay? Let's force the intercept to be 0. Okay? Now, what's a reasonable, okay, how tall am I in centimeters? What, about 180? Yeah. And I weigh about 70 kilos. I think. Is that right? I really know my weight in pounds, not kilos. I'm just at that wrong age where they switched from imperial to metric when I was in grade 4, so I don't know any measuring system. Let's see, 70 times 2. Nah, not 70. Let's go 80. Say I'm 85. No, 85 is about right. So, we're doing this based on one data point, me, as I am the platonic state of humanity. My Schwarzenegger-esque physique. So, I don't know, let's say, so we got 180, and we got 170, 85, so 180 in our case, so we're going to make it, so we got weight by predicting weight from height, so times, predicting weight from height, 176 divided by 5, it's 2.0. That's good. Okay. So we say weight equals about 0.5 of height in centimeters. Weight in kilos equals, I don't know if that's true. We're going to use that as a rough estimate. Okay. Now, we can then make predictions, and that's fine. And I come out to be in perfect shape with this model. So, that's all well and good. Everybody's happy. And of course, we would probably do multiple regression here, or we'd have 2 regressions, one for women, one for men. We'd probably have 4. We'd have one for women, one for men, one for girls, and one for boys. Little girls and boys. But that's good. Who cares? Let's pretend that we're all the same. If we change this is what we care about. If suddenly it comes out to be 12, because we violated the assumption of multicollinearity, well then I'm, let's see, that means I'm way underweight and I should start just eating handfuls of butter. Just handfuls of butter.
That's disgusting.
And pork fat.
That's disgusting.
Even better, duck fat. God, I love duck fat. You don't like duck fat? You can buy duck. You fry potato. Here's a tip for you all for cooking. You can buy duck fat in the store, or you can render it from a duck, which is a little more time-consuming, but you get a duck at it, which is nice. If you fry potatoes, for example, in duck fat. Oh man, it's even better than frying it in beef tallow, which is really good. But duck fat is the only way to make French fries. It's really expensive way to make French fries, but it's delicious. Or you could take, anyway. Duck fat, you give me duck fat and beef marrow, I'm happy. I ordered one of the appetizers I ordered the other day when we were at the dinner for the thesis students. I ordered the veal marrow. God, it was good. Anyway, I'll probably leave right now and just go to a restaurant and order that. I'm back now. We don't want this to change! We don't want the beast to change. Even though it would mean perhaps the prescription from an MD to eat duck fat. So, how many times can I say duck fat? Today's title of the podcast, how many times can I say duck fat? We don't want that happening, because that's actually what we care about. See why these coefficients are important, right? Because that's what's allowing us to make a prediction. So we got to detect this multicollinearity. That's the thing. We have to know what's happening so we can do something about it. Well, the first thing to do is we can just look at the correlations between the x variables. And a lot of times when you start out what's called building a regression model, you have all these x variables. You might have collected one y variable you want to predict. Right? And I mentioned before my friend Todd doing this stuff, predicting the number of cigarettes people smoke per day. And he had that and 22 other variables that he measured. He came up with eventually a 4-variable model that was as good at predicting how many cigarettes people smoke per day as getting blood levels of nicotine and getting salivary levels of nicotine and cotinine, which is a stable metabolite of nicotine. But people don't want to do that. People don't want to spit. Well, they might want to do that, but then the MD has to take it off to the lab. It would be better if I could ask you 4 questions and then I know how many cigarettes you smoke. Way quicker. Way less invasive. So he had number of cigarettes you smoke a day and then 22 other variables. Wow. So he's got 22 variables. You can't build a model with 22 variables. It's useless. It's too complicated. You want to be able to explain a lot of variance, right? But you're going to have a lot of correlation between them. Like he had one of the variables that ended up in the final model was time to first cigarette. How long till you wake up? After you wake up, do you have a cigarette? Right? But that's probably going to be somehow correlated with what year did you start smoking? Like how old were you? It's also going to correlate with how many years have you been smoking. That's going to correlate obviously with how young were you when you started smoking, how old were you? They're going to overlap. They're going to be some of the same variance. And you don't want that. So one of the first things you do is you look at all the correlations between the x's. Just regular Pearson correlations. And you probably have to chuck some variables. You probably have to make a decision and say, which one do I not want? Now, how do you do that? Well, you look at something and say, okay, this one overlaps, like x1 and we had x1, x2, x3, and x1 and x2 correlate by 0.2. One of those has to go. Which one correlates more with y? Or correlates less with other variables? And you just throw it away. Of course, if you're smart, you do it two ways. You throw one away, then you throw the other away. Try both of them, because it's usually not that clear. So multicollinearity, you cannot violate the assumption that there's no multicollinearity, or that the assumption really is that it's a completely additive linear model. Another assumption is that it's linear, that it's about straight lines, that it's a coefficient times a variable A. We assume a linear model. What if it's not linear? What if the relationship isn't linear? Like, for example, a lot of drug stuff is, like dose response curves are almost always parabolas. Usually upside down parabolas. They're curves like this. So they're curves, they're not straight lines. You can do something called curvilinear multiple regression. It's perfectly acceptable. It's just hard to do. Because you have to know, and you have to actually know what shape it is. Assuming something's a straight line is easy. And most things are straight lines. You care about it. But what if it's not? Oh my God, what is that? What if it's the case that y, in the real world, that y equals, that looks like it's, I think, is that a lambda? Lambda sub 0 to the lambda 1 x e. All that is it's an exponent. The lambdas, I'm using those instead of betas because it's not a straight line, so we use betas for straight lines. But what if the world was like that? What if we had a relationship like that and we didn't know what to do? Well, there's a couple of things you can do. The first thing you do, you quit. Say, I'm done. I don't want to play anymore. I'm going to become a poet. They don't do any stats. But you probably are interested. You're probably interested in what happened. You collected all these data. So the first thing you would do is go, ah! And then, actually, if you took the logarithm, oh, look at that. If you took the logarithm of that thing, that monstrosity on the last page, you get log y equals log lambda sub 0 plus log lambda sub 1, x sub 1 lambda sub plus log e. Oh. And you know what? Mathematically, one of the things you can do, and you were all taught this in high school and have now all forgotten it, is you can drop, as our teacher used to say, you can drop your logs, and we would always go, so you can't. You can now go, take all the log bits out, and then suddenly, look, it's linear. Oh, Cassie.
I say it's funny, the girl in another classroom opened the door and looked down the hall after you screamed.
Yeah?
Yeah. For danger.
Danger. You want to see I am the danger. Breaking Bad reference for you. We're having fun. There's science in here. I'm just screaming. No one said there's no crying in science, but there is screaming. So what we have here, in fact, is a relationship that is not linear, but it's intrinsically linear. We can turn it into a linear relationship simply by using a mathematical transformation. So an intrinsically linear regression is a nonlinear relationship, or an intrinsically linear relationship is a relationship that is not linear, but that can be transformed into a linear relationship. And that's what we get here. It's an exponential relationship, but you can easily, through taking the logarithm of something, turn it into a linear relationship. That's easy. For example, a lot of you guys have seen a slide that I use in neuropharmacology, which is the relationship between D2 binding efficiency for antipsychotic drugs and the ED50 for antipsychotic drugs, and it's a straight line, except it's actually not a straight line, it's exponential. But to do it with regression, what they do is they take the logarithm and it becomes a straight line. It's mathematically completely sound and it's completely sensible. You just can't do multiple regression on a line that looks like this, or even univariate regression. That's what that line looks like. But if I take the logarithm, that turns into a straight line. Beautiful. Beautiful. A lot less screaming than you might expect. Now, not everything is intrinsically linear. So when you have an exponential curve like that, it's fixable. It's completely fixable. On the other hand, when you don't have that, when you look at some funny relationship, you don't know. You oftentimes won't know if it's intrinsically linear or not. If you see this, you go, "Oh, I can fix that. That's an exponential curve." If you see a curve that looks like, I don't know, like that. Remember your functions that look like that from high school? That's a quadratic equation. You can't fix that. That's a quadratic. That's like y equals x squared plus 2x plus 3. That can't be fixed. Now you have to fit a curve, and you can do this. You can't do it, but a computer can. I couldn't do it, but a computer can. I have to tell the computer, "Oh, don't fix. We're not using straight lines anymore. Our model is now a weird quadratic equation." Doesn't happen that often. But if you see that, relationships like that do exist in life sciences, not a whole lot. That's more of something you see in physics. Okay. So that's all fixable, right? But not always. It might be the case that there's nothing we can do. So we're also assuming, as I said, a completely additive model. There's no mention of interactions. There's no mention of x1 times x2, or remember we had alpha, beta, x equals beta plus alpha plus beta plus alpha, beta plus epsilon. You could add something in. You could add in x1, x2. The thing is, and a lot of you guys asked me before, when we were talking about analysis of variance, when you have that a by b alpha beta term in the model, is that actually is that actually multiplication? I would say not really. Here you're actually saying mathematically you're multiplying the value of x1 times the value of x2. So when you're saying something like that, it's tough to know what that term should be. Should it be x1 times x2? Should it be perhaps x1 to the x2? It's hard to know, and this is where exploratory data analysis is really important, and actually a really good feeling for things like, for mathematical things, for like functions, which you may not have, but there are always people around you that have that. If you think there's an interaction, or there should be an interaction term. Or you can look at past research. Okay. So one of the things we want to do is we want to select the best variables to explain variance and why. So if we have qualitative predictor variables, right, like hair color, might be a thing, I don't know. or sex, male, female. Sure. That's often, we think of sex differences. Sex, things that are qualitative are fine if they're binary. Remember that you have to be able to do math with these things. So you can't put, it can be y hat equals 7 plus 3 times hair color, because what's 3 black mean? Doesn't mean anything. So if it's binary, it's actually pretty good, because if it's binary, we can code and do what's called dummy. Well, I'm going to show you a thing called dummy coding. What you do is you just pick one value and call that 1. And the other value, therefore, is 0. So if it's male versus female, right? We just say, let's make this a measure of maleness. Males get 1, females get none. Don't get all sociological. I'm talking about Y chromosomes you own, okay? You have 1 or none. And yes, I know people sometimes have 2 Y chromosomes. Yeah, that's really, really vanishingly rare, okay? Male 1, female 0. Or if you think that somehow is oppressing you, female 1, male 0. I don't care. Okay? If y'all feel oppressed, check your privilege, man. So that's easy. 1s and 0s. 1s and 0s. You can do that. That's really easy. How do you do it if you've got something where it's not binary? Because you might collect data like that. Oh, by the way, use 0 and 1 and not 1 and 2. Because you couldn't use like 1 for female, 2 for male, because that's saying that male is twice the male that female is. It doesn't make any mathematical sense. You got to realize this is actually doing math here. So 0s and 1s actually make sense. One of the problems we often have is and I'll talk a bit about how to fix other cases that are qualitative. We use Likert scales a lot in psychology. 1 to 7? Right? Strongly disagree, strongly agree. There's a problem there from 1 to 7. The biggest issue in that is 7 times the response that 1 is? I don't know. Even a sum Likert scale. So you've got I don't know, what's one of them surveys? They do cognition research. Tell me the name of a survey. I don't know any of them anymore. I don't have to know any of that crap anymore. I don't know, a personality one.
MPIA?
Which?
The
Minnesota Multiphasic Personality, MMPI. Very good. Right, the Minnesota Multiphasic Personality Inventory, the MMPI. And it's got subscales, and I think it's got a regression subscale. And if it doesn't, let's pretend it does. And you get a 26 on it. I don't know if that's right. Is 26 aggressions twice being 13? I don't know. Yeah, well, I don't know what we're measuring there. What would the unit of aggression be? You ever ways kind of around it? One of the things, one of my students this year, Jesse Merlake, what he did is instead of having people, this is actually quite cool, and this is not a bad idea, you go strongly disagree to strongly agree, and you draw a line, and then you have people tick off where they believe they are, and then you measure it. That's a little bit better, and sometimes people do that. The problem with that is then you end up to collect your data measuring lines, and it's really, really not fun. So you gotta be careful with Likert scales. Just in general. I think in psychology we should just be careful with Likert scales. One of the things you can, it's nice if we have experimental variables. We actually set up an experiment rather than just collecting a whole bunch of data. We actually put people into groups, and they can be 0 and 1, and are they in a group or not? And there's never going to be any multicollinearity between things that we've assigned to people. So they're kind of nice for experiments. Now, what do you do, though, in a case where we have hair color? What do we do in a case where we got hair color? And there could be a variable we could measure. It's conceivable. Or we could measure, I don't know. Yeah, hair color probably wouldn't come up so much. But what about mother tongue? Language you speak. Like the first one you learned. Right? Everybody here learn English first? Their first language? Everybody? Yeah?
No, I didn't.
Okay, good. What's yours?
Nepali, but I like forgot it.
Yeah, it's fine. But we got a different number. That's good. Anybody else? Oh, good. What's yours?
French.
French. Excellent. So we got a French and Nepali. This is good. And then a bunch of people spoke English first. Is that correct? Everybody? Okay. I don't care. No one's getting any extra points for having a different language. But let's say we're doing something with our class, and we measure. One of the things we want to measure is your mother tongue, because we're doing something to do with learning something. How in the hell are we going to get that mathematics? Because we can't go 1, 2, 3. We can't go. Nepali is twice the Frenchness that English is. That doesn't make any sense, can we? We can't do that. We could, however, have a variable called Englishness, or Englishosity, or Anglo-learned. Let's go with that. A. I get a 1. Let's see. Spence gets a 1 because he didn't say anything, so we're assuming he spoke English from the beginning. Jay gets a 0. See how that works? Okay. Then we go with Nepaliosity. We get 0s. Jay gets a 1. Oh, now you see what we can do? Oh, we can do Frenchness. So we got 0, 0, 0, 1. Pretty cool. So this is called dummy coding. You end up, instead of having one variable called mother tongue, we have to have 3 variables, one called Englishness, one called Frenchness, and one called Politonian.
I don't actually like that ice cream.
This is neat because you can even have somebody, now, for example, this is cool because you can even have somebody, in this case, we can have somebody, let's pretend that Madeline was in this class and wasn't just marking your papers, she was also in the class, which would be a huge conflict of interest. But in her case, she would get a 1, a 0, and a 1. Pretty cool. So we could deal with somebody who was raised bilingual. That's neat. Because you went both at the same time. Okay. Did you go both at the same time? Or you just
No, my French was first.
Okay, yeah, nice. When did you start speaking English?
Well, see, my grandma babysat me because my mom and my dad worked all the time, so I
Okay.
started speaking French before.
Okay, interesting. I think Maddie's French was quite stronger than her English when she was young. Really young, but then she would switch back and forth, but she'd speak, she would never, I never remember her putting the other languages word in a sentence unless you didn't know the word in the other language. Our cats were all, we had 3 cats. Every animal was a shot. Every animal. Dogs, people should know. That's not true. That part wasn't true. So you see, you can do this dummy coding. It actually works. The problem is now we got all these extra variables. So if we had more than, let's say it's 2, we have 3 languages, which is 1 more than you normally expect in a Canadian classroom probably. But if we could have, what if we had like 5 different languages? Suddenly we have 5 variables, not 1. So this can sort of a diminishing return here. But dummy coding is cool. Okay, so we've got all the data. We've got reams and reams of data. The cigarette, I still actually have the cigarette per day data set. I have an SPSS data set, and it's a real. When we taught this, I taught this class in Newfoundland. There was an actual complete lab section that had nothing to do with the class. It was just SPSS, and their final assignment. Dwayne did this assignment, for example, was find the best model. That was all it said. So they had 500 records, so 500 people, with the number of cigarettes they smoked per day, and then 22 other variables. And I was just saying, find the best model. That was all it was. Wow, doesn't sound easy. You know what? Actually, the class would either come out with a 4-variable or a 7-variable model. Everybody would always come up with the same, which was pretty good, because you learn how to do this. You build a model. So how do you choose which variables to use, which variables not to use? Because they're all going to contribute to some of the variance. This is different from ANOVA. We're making a prediction with multiple regression, which I've capitalized for reasons that escape me. We're making a prediction here. So you start with a lot of variables. And like I said, with the cigarettes per day example, we're starting out with one predicted variable and 22 predictors. And in that case, you want, and again, as I said, in that data set, one of the things we had two physiological measures: salivary nicotine and salivary cotinine. And typically, what they do to determine how many cigarettes you smoke a day is they take a saliva sample and measure the amount of nicotine, measure the amount of cotinine, and they basically use a regression model. There's a model that's been built, I don't know, 85 years ago, and it says that's how many cigarettes they smoke per day. It does a pretty good job. Now, what you want to do is use all the behavioral things and come up with something that does a better job than that. So something you go into a doctor's office and they say, I got 5 questions for you. Okay, you smoke this many cigarettes per day. Because I can tell you something, anybody here who smokes knows this, you underestimate how much you smoke. When you go to quit smoking, one of the key things to do is to count how many cigarettes you smoke per day. And the first time you do that, you go, holy crap, I didn't think I smoked 35 a day. I thought it was more like 20. Right? That's just screwing around, that's all. Go figure. Oh, you want to smoke properly. Screw the Olympics, go pro. I mean, it's... So, what Todd did is he actually gave people these little journals and they counted how many cigarettes they smoked per day, and then it was pretty cool. And he was able to build this model, which was more accurate than using their saliva sample. So, one of the things you could do is you could do all possible regressions. Okay, so if you got 3 variables, there are 7 possible models. Whenever I say this, I'm including the intercept and I'm including residuals, obviously. x1, x2, x3, x1, x2, x1, x3, x2, x3, x1, x2, x3. There are 7 of them. Yeah, why not look at all 7 and see which one does the best job predicting with the least amount of complexity? Sure, you can do it with 3 variables. With 4 variables, there's 15. Okay, it's a little bit more annoying, but you got 15 of them. With 10, there's like a zillion. I think it's actually a zillion. With the 22 variables, and I would give this assignment every year, I would say you could do every possible regression, please don't. Your computer, there's not that much paper literally in the universe. And when I taught this course, when I taught it at U of T as a graduate student, and I said to the class, here's your assignment, find the best model. Now remember, don't do all possible regressions. And of course, some idiot always does all possible regressions. And I remember my class made a mainframe U of T crash. So I kept getting calls to the lab. Is Professor Broadbeck there? And I go, yeah. One of your students, they're doing it again. Also, they're using 200 pages of printing a term. I know the world's so different. And they start printing them all out. So all the printers in the whole university are taken up with some idiots printouts that are printed everywhere, buildings all over the city. It's like, I explicitly told them not to do this. I'm sorry. So you can't, practically, almost always the case, you can't do this. One of the things you have to do is, no matter how you're looking at them, you have to look at residual plots. So the residual plots here are very useful. I talked about it when I talked about single regression. And this is when you look at an x variable and the residuals. And they should be random and independent. You can find anomalies. You could find a funny, plot. I don't know, let's say you did a residual plot. Like this. So, and your software will print out residual plots. For diagnostic purposes, no problem. So you've got residuals here, you've got x variables here, and you got 0 here. And you want something where it's uniform and unpredictable. So I can't look at the x and say, oh, I know where the residual should be. So it shouldn't be getting bigger or something like that. You can also spot something like this. There's one up there. What the hell's going on there? That's a weird data point. So you can isolate that and say, why did that happen? And it might be a coding error on that in that smoking data set, one of the problems is there are a few coding errors. And one of them, people were asked how many cigarettes they smoked per day, and one guy said 400. You can't smoke 400 cigarettes a day. I don't think there's enough time in the day. You smoke 40. Probably 40. It's probably 40 and someone's fingers slipped and they were putting the numbers in, right? But
How long does it take to smoke?
400,
It would take me like
40 is basically what? 2 small packs of cigarettes.
to 7 minutes.
400 is 20 small packs of cigarettes. It's 2 cartons of cigarettes a day. You can't smoke that much and live. So it's probably 40, but you throw it back as data because it's a mistake. Because you can't fix it, you can't go, it's probably a coding error. It could be, it is possible. When my dad was in the hospital, he broke his back in 1966, and he was in the hospital down the street. I was born. My poor mom was sitting in a city she didn't know, alone with a little baby. My dad in the hospital for 6 months. And there was a guy, and we shared rooms, 4 guys in the room, and one guy who was in there who smoked so much. Of course, you could smoke in your hospital room back then because it was the Mad Men era, and everybody smoked everywhere. But this guy was always smoking. He was finally told because he was in there for like lung cancer. It was actually laugh. But and the doctors were like, and the nurses were like, don't give this guy any more cigarettes because they were all trading cigarettes with him. It was like prison really. And but this guy, Dad said, probably smoked half a carton a day, right? And then at night when they stopped giving him cigarettes, he would sneak around into ashtrays and then empty all the butts into a big piece of paper and smoke it. That's not screwing around. That's like, I kind of have a little bit of admiration for that kind of behavior. So it's possible perhaps, but unlikely that the person smoked 400 cigarettes a day, and that would show up here. It's like, what's going on? Why is that point there? Right? So you can spot an anomaly, and you can spot nonlinear relationships. Like, what if this thing went like if the sort of cloud of residuals, we call it, was like that? Well, then that means it's probably a curve, not really a straight line. We got to do something about that. All right. You might think there's got to be a way to do this automatically. Yeah, there are ways to do this to automatically pick variables. There are basically 3 simple ones. The first is called forward selection. It's an automatic method of picking predictors. You start with the x that has the highest r squared. So in our case, of our own example, x1 goes in first. So it's the one that has the biggest correlation with y. Now you add the next variable in that gives the next biggest jump in r squared. You can see you can do this by hand, but you'd be testing maybe 20. It's impossible. Why not let the computer do it? Keep on going until the jump in r squared is not big enough. Because it's always going to go up. Remember, r squared is always going to go up. It can't go down. Just r squared can go down, but big R squared cannot go down. And you might say to yourself, oh, not big enough. How precise is that, Dr. Statistics boy? Well, you could actually do it this way. There's this thing called, whoa, don't do that. Let's go back. Okay. This thing called F star. What's F star? It's mean squared regression for x1. Oh, look, there's suddenly those type 1 and type 2. Type 1 and type 2 sums of squares are actually useful. X1 given x2's in the model divided by mean squared regression for x1, x2. In other words, this is seeing how much extra variance is accounted for by x1. There are defaults that are set in software for how big this thing is. Don't screw with them. Unless you really know what you're doing, you don't mess with them. Because they're sort of standards. So all this is saying is how much extra variance is being accounted for by x1 on its own. That's nice. And that's how we determine not big enough. Is it a significant jump? And it's looked up. It's basically distributed as F. It's just an F test, really. So it's called F star. So, and then you stop. When it's like, oh, not enough, we stop, done. Model, done. Yay! That's one way to go. What about if we went the other way? What if we did backwards elimination, which sounds like something that might show up on Big Brother? Is that still on TV? Why? I mean, arguing cases you can't, right? It's useless. It's silly. But it's just to me an indication that Western civilization is almost dead. Backwards elimination is exactly the opposite. Let's do the opposite thing. Let's put all the variables in, put them all in, and then start dropping the ones that contribute the least. And keep going until you take out a significant amount of variance. So the smallest F star. You keep going until it's like, oh, the F star's too big now. Quit. Here's a model. Woo! Science. Well, so stepwise, people love stepwise. This is huge. Actually, it combines both of them, which is kind of cool. You might be surprised to know that forward selection and backwards elimination don't always agree with each other. You think, huh? Yeah, they don't always agree with each other. They'll come up with two different models. Let's put the two together. Let's put the two together in a sort of coalition government. So, let's combine the two. Let's go forward. So we start with forward selection. Biggest F star. Check F star. Put another one in. Now let's check them all again. Now suddenly we've got X1, X2, X3, and then we bring X4 in, and then suddenly X2's F star is no good anymore. Well, throw it away! Yeah, that's good. We could do that. That sounds like a compromise solution. That sounds great. So you keep going. You set the criteria for adding and dropping, and this is another case where don't screw with the defaults. Because you have F star to enter and F star to leave. The F star to enter has to be greater than or equal to the F star to leave. Because if it's gone the other way, the software just gets caught in a loop. It's like, put it in, take it out, put it in, take it out, put it in, and just keeps going. And again, this is one of those things I always tell the students, please don't mess with those. They just leave them the way they are. And someone's always like, well, I'm really smart and I'm going to play with the defaults. And then their computer locks up. Using all their processing cycles. I can't even torrent a movie in the computer lab. So I've heard people do that. I'm not saying you should. I'm saying I know it's done. Do your torrenting at home using an anonymous proxy. But don't mess with that. See, the thing about this is that the automatic methods only look at those Fs. That's all, the F stars. That's all they look at. They don't look at residual plots. They don't really look directly at multicollinearity. If you've got two variables that overlap, the F stars get smaller, fine, but they don't really directly look at multicollinearity. They're just automatic things based on one criterion, which is F star to enter or F star to leave, depending on the method. They don't care if it's a nonlinear relationship. They don't look at those things. I bet you could build an algorithm nowadays that does that, but I mean, one could. I couldn't do it. They don't do any of this stuff. This stuff that, in fact, you should do on your own. You actually have to use your eyes, right? And look at plots and go, that's weird. And you have to look at correlation matrices and say, okay, those two variables correlate too much. I can't use one of them. So here's an approach that I've done. I've used regression very rarely, but I have. Start with a correlation matrix. Get all your X variables and your Y and a correlation matrix of all of those things. Pick a subset, right? You pick a subset of values, of variables. You're never going to pick them all. You're going to look, that correlates 0.05 with Y. Why would I even try putting that in the model? That's useless. That's not good. I'm not even going to, and you can usually get rid of a bunch of variables that way. Or you look and say, these two correlate with each other, these two x variables, one of these probably has to go. Which one? And if it's small enough, do all the models. Like you can see if it's 4 variables, yeah, just run them all. Look at all of them. That's easy. I would run all 3 automatic methods because they do that. They do the variance accounted for thing really well. And now I've already done the correlation matrix. I've already taken out the ones that are correlated with each other. Always check for outliers, look at residual plots, see if you've got linear, nonlinear relationships. We're assuming, by the way, that I've done exploratory data analysis. Before I've done this, I've looked at every variable's scatter plot with y to look for nonlinear relationships. And I check for outliers along the way with residual plots, and then I put it away for a week. And I come back, and I do the whole thing again. Because you're going to miss something, probably, because this is more, it almost gets to the sort of more art than science angle. You're going to miss something. You're going to miss something. So just do it again. And you will come up with a somewhat reasonable model, a defensible one. Someone else might come up with something different. But like I said, when I had my students in the past just play with a data set, half of them would come up with one model and half with another one. And neither one was wrong. You could defend either of them. You can defend either of them. Another thing you can look at along the way is you can look and see if the model is biased. When I say biased, I mean, is it over-predicting or under-predicting something? Now, how are we going to know that if we don't know reality? Well, we can't really, but we can. There are ways to do it sort of theoretically. And one of the things to look at is a statistic called CP. Okay? Now, the expected value of CP equals P if the model is unbiased. Now, what's P? Well, there are P minus 1 predictors. There are P minus 1 predictors. So it's the number of predictors plus 1. So if we have we have a model that has x1 and x2 in it, if we have an unbiased model, it should give us a CP of somewhere around 3. If we have a 2-variable model, it should give us something around 3. Okay? For example. And that's a statistic I, for the life of me, don't know how it's calculated. But I can tell you that it's spat out of every regression piece of software, and it's a thing that a lot of people ignore, and it's a way to just detect bias. Is a model over-predicting or under-predicting? And it's only one piece of information. And it's also useful. I just don't have this on the slide. I thought I'd mention it now. Do you have questions about what we've talked about today? All right.
Can you do an example? Or no?
No, I really can't. I wish I could. But if we had, actually, what we would have is something like, let's think of it this way. Let's do something mythical where we have 3 variables, x1, x2, and x3, and x1. So we're going to see how they correlate with each other. That's where we're going to start. So that we can't do that, we can't do that, we can't do that. 5, that's 2 and 1, 1, 2, 3, 5. 3 and 1 is 0.05. So that means 1 and 3 is 0.05. And then, okay, so for example, here's a correlation matrix. I would look at that right away and go, oh, x2 and x1 are correlated with each other. They're supposed to both be predictors. Do I want those 2 variables predicting each other? Or do I want 2 x variables that overlap like that?